Jai Hind, myself Pushkal, Assistant Professor in Computer Science Department, AKGEC Engineering College, Ghaziabad. Today I will discuss Theory of Automata in Formal Language, BCS 402. This subject is important for the 4th semester second year students of CSC, CS, IT, CSIT, CSC, DS, AIML as students of BTech students. So I will discuss Theory of Automata. So what is objective of this topic of finite automata? So the objective of this topic is to make students able to understand the requirement of the finite automata, implement finite automata, realize the expressive power of epsilon NFA, NFA and DFA, and also the difference between the DFA and NFA, and how to minimize the DFA, how to minimize the DFA or FA, how to minimize the NFA, that is how to minimize the FA. The term automata is the Greek word. This is the Greek word which means self-acting. And the plural of automation is automata. Automation is a singular word and its plural is automata. And automation is the system that performs some function without human intervention. It is a machine which takes inputs, processes it, and provides outputs without intervention of human beings. It is the study of abstract computational machine and the computational procedures that solve computational problems by using these machines. Abstract machines are mathematical model of real computation. There is input, this is output, here is a CPU, program memories are there, and temporary memory is there. This is the basic abstract model of the automata. So it takes inputs, process it based on the written instruction, written program in the program memory, and it provides the outputs. For example, suppose we have to compute this fx equal to x square plus 3. So here we see fx equal to x square plus 3. So we can break this y equal to x into x. This is an intermediate. Y will take an intermediate variables, your temporary variables, and x into x is going to store in this variable y. So we have to write a program in the program memory y equal to x into x. Again, this y is going to write here y plus 3 fx equal to this. So we write a instruction in the program memory y equal to x into x and fx equal to y plus 3. These instructions are written in the program memory. If we pass the input x equal to 5, the value of x 5, so the instructions are given in the program memory. So what CPU will do? It will pass x equal to 5 into this, and this calculation is done in the temporary memory, and y equal to 5 into 5, so value is coming 25, and this 25 is passed to this fx equal to 25 plus 3. So all the calculations are done in the temporary memory and the result will be coming 28. So by this way computation is performed. So based on this temporary memory we are going to distinguish different kinds of automata. So finite automata is distinguished by the temporary memory. It means no temporary memories are there in the finite automata. Here we will see if this memory is not there in the finite automata. All things are there, input is there, this CPU, program memory, output, all should be there, but this temporary memory will not there in finite automata. In a case of push down automata, there will be a temporary memory that is known as the stack, in which push and pop operation will perform. And again Turing machine, there is also a temporary memory that is known as the random access memory. If you talk about the power of automata, so we see a most powerful machine is a Turing machine, which can solve any algorithm. This is a most powerful, and it can solve any types of computational problems like any algorithm. Push down automata, that having a less power as compared to the Turing machine, and finite automata is very less as compared to push down automata. So this is less power, and this is the highest power, more power. And push down automata is in between the finite automata and the Turing machine. Now come on the application of automata theory. So if you talk about the application, so automata theory play an important role when you are making software for designing and checking the behavior of the digital circuits. Software for designing and checking the behavior of the digital circuit. This is the application of automata theory. Second, it can work as a logical analyzer of a compiler. We know there are 6 phases in the compiler. One of the important phases is the logical analyzer. Compiler breaks down the input text into the logical units like identifiers, keywords, and punctuations. Third application, we see software for scanning large bodies of text such as collection of web pages to find the occurrences of the words, phrases of the other patterns, etc. And fourth application is the most useful concept of the software for natural language processing. Natural language processing. So these are the application area of the automata. Now, the common term used in the automata is alphabet. Alphabet, that's very important. An alphabet is a finite, non-empty set of symbols. For example, 0, 1, A, B, like finite, non-empty set of symbols. Like it is represented by sigma. So, for example, sigma equal to 0, 1. So it is a binary alphabet. It is a binary alphabet. Sigma equal to 0, 1, 2 up to 9. This is a decimal alphabet. Decimal alphabet. Sigma equal to A, B, C up to Z is a lowercase alphabet. Sigma equal to 0, 1, 2, 3 up to 9, then A, B, C up to F is a hexadecimal alphabet, and so on. So alphabet is a finite, non-empty set of symbols. Strings are words. A string is a finite sequence of symbols over alphabet, sigma. A string or word is a finite sequence of symbols over that alphabet. For example, W equal to 10110 is a string over 01. W equal to AB is a string over alphabet sigma equal to AB. W equal to XYZ AB is a string over alphabet AB up to Z, and so on. So we can say a string is a finite sequence of symbols. It is a finite, non-empty sequence of symbols over alphabet. Length of a string. So length of a string, it can be represented by this. The number of symbols present in that string is known as the length of the string. So length of the string is, suppose W equal to AB, AB, AB is string. So length of the string mod W equal to 1, 2, 3, 4, 5, 6. Six symbols are there. So the length of the string is 6. Next, power of sigma. So sigma to power k is the set of strings of the length k. Suppose for example, if we're talking about the power of sigma, so sigma, suppose sigma equal to 0, 1. Then sigma के power 0 equal to lambda या epsilon या reverse V. We can write anything. Different books have written this lambda, someone has written epsilon, and someone has this symbols. Yani empty string. So if sigma equal to AB, then epsilon, sigma ke power 0 equal to epsilon, called the epsilon, right? The same way. Sigma ke power 1, in this example, sigma equal to AB, so sigma ke power 1 will be AB. Sigma ke power 2 will be this. How it can come? For example, suppose sigma equal to AB. Then sigma ke power 2 will be sigma dot sigma. So this will be AB dot AB. So AA, AB, BA and B. AA, AB, BA and B. So this way we can compute. Sigma ke power 3 will be sigma square into sigma. So this will be AA, AB, BA, BB. Sorry. Sigma ke power Q equal to sigma square into sigma. So this will be AA, AB, BA and BB. So this will be AAA, AAB. So this will be AAA, AAB, ABA, ABB, BAA, BAB, BBA, and BB. So here 8 strings should be there. By this way we can compute sigma ke power n या sigma ke power k. Then reverse of a string. Suppose W is a string, then the reverse of a string is represented by W ke power r. For example, if W equal to x, y, z, then WR, reverse of a string is ZYX. 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 Flipping the last symbols. Substring of a string. If W equal to x, y, z, then its substrings are epsilon. Epsilon is the substring of every string. Then X is the substring of x, y, z. Z is substring of x, y, z. Y is also a substring of x, y, z. X, y is substring of z. Y, z is substring of z. Z, x. X, y, z is string of y, z is substring of x. Prefix of a string. If W equal to x, y, z, then its prefix R. Epsilon is the prefix of x, y, z. X is the prefix of XYZ, XY is the prefix of XYZ, and XYZ is the prefix of XYZ. So there are the 4 prefixes of XYZ. Similarly, suffix of a string. If W equal to XYZ, then its suffix are lambda, yeah, epsilon, lambda, yeah, epsilon. Both are same. Z is the suffix of XYZ, YZ is suffix of this XYZ, and XYZ is the suffix of XYZ. So there are also 4 suffixes of string W equal to XYZ. And here, very important, lambda, yeah, epsilon is also a prefix and suffix of a string. Languages. A set of strings over sigma is called a language. A set of strings. For example, there is a language L1 equal to W equal to 0, 1 star. W has equal number of zeros and 1. So possible strings are equal number of 0 and 1 over an alphabet. Any combination of 0 and 1 will be equal number of 0 and 1, that is 0, 1, that is 1, 0. Equal number of 0 and 1 are there. 0, 0, 1, 1 should be there. 0, 1, 0, 1 should be there. 0, 1, 1, 0 should be there. 1, 0, 1, 0 should be there. All these strings will be in the part of the language. 1, 0, 0, 1, 1, 1, 0, 0, and so on. L2 equal to W is element of A, B star, and W mod W is less than equal to 3. Yani ki all those strings which having length less than or equal to 3, that will be based on, here we have to write based on 0 and 1 should be there. This is wrong actually. 0 and 1. And having length less than equal to 3. So epsilon should be there. Have length 0. That is 0 is also there. 1, 0, 0, 0, 1, 1, 0, 1, 1. So all these strings having length less than or equal to 3. So that's it. So this is the language. Now clean closure, that's very important. So clean closure represented by sigma star is the set of strings of all possible length including lambda. Clean closure is represented as a sigma star is the set of all possible strings of all length including empty string. So this will be sigma star will be, this is a set of all strings of all length, yani in 0 length. This is what set of strings of 0 length. This is a set of strings of length 1. Set of all possible strings of length 2. Set of all possible strings of length 3 and so on. So this is what? This is set of all strings of all possible length including 0, 1, 2, 3 and so on. So this is sigma star. So sigma star is also known as the clean closure and it is represented by sigma star is the set of strings, set of all strings of all possible length including 0. And 0, V, 1, 2, 3 and so on. For example, sigma equal to AB, then sigma star will be 0 length, that is empty string, that is epsilon. 1 length, A and B. 2 length, AA, BB. AA, BB, AB, BA, all should be there. 3 length, AA, AB and so on. So this is sigma star. Positive closure. So positive closure represented by sigma plus is the set of strings of all possible length excluding, yeah, this one is excluding empty string. empty string. This term is missing. Positive closure represented as sigma plus is the set of strings of all possible length excluding empty string. So this will be, we know sigma star equal to sigma 0, sigma 1, sigma 2 and so on. And sigma plus equal to, this part will be excluded. So this will be sigma 1, sigma 2 and so on, sigma n. Here we see a sigma plus equal to sigma star minus this. This is known as lambda, yeah, upside. Yeah, we can say this will be written as sigma star will be sigma 0 union sigma plus. This is very important. For example, if sigma equal to AB, then sigma plus will be all possible strings of all length excluding empty string, any epsilon. So epsilon part will be not there. So all length, yani 1 length, 2 length, 3 length, 4 length, 1 length, 2 length, 1 length, this is 2 length, this is 3 length, 4 length, 5th length and so on, excluding empty string epsilon. But in case of sigma star, if you add this in this, so it becomes a sigma star. And if in a sigma star, if you exclude this, then it becomes a positive closure. Now, finite automata. Finite automata, it is a mathematical model that works for several computer algorithms. It is a mathematical model that works for the several computer algorithms. It is called finite because it works on finite set of input symbols. Here input symbols are there. This is known as the input tape, where input symbols A, B, A, B, A, B, A, B, A, B. So this is the finite. This is a finite. This works on the finite set of input symbols with the finite number of states. A finite control, finite sets are there. Q0, Q1, Q2 up to Qn. So here the finite states are there and finite input symbols are there. That's why it is known as the finite automata. And it produces outputs in a finite times. So that's why an automata is said to be finite, because finite input symbols are there, finite states are there, and it produces outputs in a finite times. Here, this is the basic model of the finite automata, in which input symbols are written in this magnetic tape. There is a reading heads which is aligned at left position. This is a finite control in which different states are there, Q0, Q1 up to Qn, and based on this input symbol that is to be read by scanned by the reading head, the finite control changes their states and it produces the outputs. This is the working of the finite automata. There are two types of finite automata. One is deterministic finite automata, that is known as the DFA, deterministic, and second one is non-deterministic finite automata, that is NFA. Yeah, this is also known as the NDFA, non-deterministic finite automata. Yeah, NFA, and this is deterministic finite automata. Now DFA. What is DFA? Deterministic finite automata. For a DFA, the machine moves to a particular unique state from a given state and a given inputs. For example, there is a given state Q0 and a given input A, input symbol A. It goes to the Q1. For this particular state Q0 and a particular input B, this goes to the state Q2. So this is deterministic, fixed, where it will go to the next state. For a particular state and a particular input, where the machine will go. It means it is fixed. It is deterministic. That's why it is called deterministic. So for a DFA, the machine moves to the particular unique state from a given state and a given input. That's why it is called a deterministic. As the number of states are finite, so that's why it is called a deterministic finite automata. Mathematically, it is defined as a 5 tuples or quantuples. DFA is a 5 tuples, that is Q, sigma, delta, Q naught and F, where Q is a finite set of states. Finite set of states. Sigma is a finite set of alphabets like 0, 1. Q is a finite set of states, means Q0, Q1, Q2, Q3, Q4 and so on. Sigma is a finite set of symbols. It means this is a transition function that is mapping from Q into sigma to Q. Q0 is an initial state and that is the element of Q. And F is the final states and which is a subset of states. And it is also known as accepting and final states. Thank you.